Welcome to our vlog. Hi guys, today in our vlog, we're gonna talk about Ian Stewart's book, Nature's Numbers. Basically, we are gonna talk about and summarize chapter 2 of his book, which is entitled What Mathematics is For. The first 5 pages of the chapter explained instincts. 4 instincts actually, of different professions of different people. The entrepreneur's instinct is to exploit the natural world. The engineer's instinct is to change it. The scientist's instinct is to try to understand it, to work out what's really going on. The mathematician's instinct is to structure the process of understanding by seeking generalities that cut across the obvious subdivisions. And these mathematical instinct that he explained is also connected to the role of mathematics in the human culture. Let me explain. Before you buy anything, maybe a freezer, he explained that buying a freezer is for preserving food. But he also explained that our thoughts goes beyond that. How much food will it store? Where will the freezer have to fit? He explains that it's not just a matter of utility. It is same with mathematics and any other intellectual worldview, be it scientific, political, or religious. Before you buy something, it is wise to decide what you want it for. He also explained acceleration, where he said that acceleration is a rate of change of rate of change. Simply, the velocity of a body, the speed which it moves in a given direction, is a rate of change. Let's go and try something bigger. If a motorcycle at a steady speed of 60 miles per hour, its distance from its starting point changes by 60 miles every hour. Acceleration is the rate of change of velocity. That amount depends not only on the initial and final speeds, but on how quickly the change takes place. Basically, on a more general term, acceleration is just a rate of change of rate of change. But because there were still some confusions in the earlier history, they had to handle the questions of rate of change. So, Sir Isaac Newton and a very independent German mathematician Gottfried Leibniz invented a new branch of mathematics called the calculus. But who wants to go into details of calculus? Ian Stewart said in the book that there are just 2 main things that mathematics is for. The first one is providing tools that let scientists calculate what nature is doing. The second one is providing new questions for mathematicians to sort their own satisfaction. There you go. That's all for me. Let's go with my friend Cheska and hear her summary. Bye.
Thanks, Gab. Anyways, as a matter of fact, mathematics proven that almost anything in the world can be calculated by So going on to the first scientist that I will introduce to you, it is no other than Gregor Mendel. Gregor Mendel was a scientist who noticing the numerical relationships with which characteristics of garden peas are expressed when they are crossbred. Gregor Mendel was also an Austrian monk who discovered the basic principles of heredity through experiments in his garden. Going on to Erwin Chergaff. Chergaff is an Austrian biochemist who discovered about the proportions of bases in DNA. Depend also on the species the DNA comes from. And unlike relative time, Newton also believed absolute time was impossible and could only be understood mathematically. So going on to way back 1994 or 1994, where the computer simulation of the evolution of the eye from an initial mutation providing for skin cells sensitive to light was published by Daniel Nelson and Susanne Pelger, wherein pattern appears whenever we look. Many philosophers have wondered why is there a deep congruence between the human mind and the structure of the universe. Is the universe made of maths? What do you think? Well, Einstein's answer is simple and elegant. Stewart thinks that nature exploits every pattern that there is, which is why we keep discovering patterns everywhere. So that's all for me. I'm going to pass it to Jairi as he introduced to you his summary of what mathematics is for. Bye!
Thank you, Cheska. Anyways, mathematics observe diverse role in our universe. Discoveries and invention made through mathematics pave way for a better understanding to our surroundings.
Through Nelson and Togo's work, we know the evolution of the ice, and our perspective can change depending on the position from which they are being viewed. One great example of this are constellations, which varies depending on where you are or where you viewed it from.
So the different resonances that the mathematics have provided us with, we can observe the time it takes for a planet to orbit, and the distance they have with each other.
As we observe the differences, we also observe that we all have a certain similarity. Of the pattern has become a reoccurring sequences through their rotational and orbital period. And that's my part. Thanks for listening. I'll turn it now to my fellow groupmate, Denise.
Good day, everyone. So I will be the last one to explain. Let's get started. Our world rests on mathematical foundations, and mathematics is unavoidably embedded in our global culture. If mathematics, including everything that rests on it, were somehow suddenly to be withdrawn from our world, human society would collapse in an instant. And if mathematics were to be frozen, so that it never went a single step farther, our civilization would start to go backward. This video is all about the goal-oriented research. If you think as many people in our increasingly managerial culture do, that process of scientific discovery can be speeded up by focusing on the application as a goal and ignoring curiosity-driven research, then you are wrong. In fact, that very phrase, curiosity-driven research, was introduced fairly recently by unimaginative bureaucrats as a deliberate put-down, because goal-oriented research can deliver only predictable results. You have to be able to see the goal in order to aim it. Moreover, goal-oriented research often runs up against a brick wall, and not only in mathematics. For example, it took approximately 8 years of intense engineering effort to develop the photocopying machine after the basic principle of serigraphy had been discovered by scientists. This kind of delay is not at all unusual in industry, let alone in more intellectual areas of research. And the impasse is usually broken only when an unexpected new idea arrives on the scene. There's nothing wrong with goal-oriented research as a way of achieving specific sensible goals. Our world is not static. New problems constantly arise. An old answer often stops working. Like Lewis Carroll's Red Queen says, he must run very fast in order to stand. So this will be the end of the video.